Hello everyone. Today we are going to study spherical mirrors. This comes under the broad topic of optics. Optics is a branch of physics that deals with the study of behavior of light with matter. Before moving on, let's first discuss what a mirror is. A mirror is an object that reflects light in such a way that for the incident light in some range of wavelengths, the reflected light preserves most of the detailed physical characteristics of the original light. Mirrors typically are made up of glass with one surface coated with a metal amalgam so as to reflect a clear image. We have already studied plane mirrors in the lower classes. Let us now study about spherical mirrors. A spherical mirror is a part of a hollow sphere, typically made up of glass, whose one side is silvered and coated with red oxide and the other side is the reflecting surface. The reflecting surface of a spherical mirror may be curved inwards or outwards. Spherical mirrors are of two types, the concave mirror and the convex mirror. We will be studying both the mirrors in detail in the following slides. But first, what is a concave mirror? Concave mirror is that mirror wherein the reflection of light takes place at the concave surface or the bent-in surface. The reflecting surface is towards the center of the sphere of which the mirror is a part. If you see over here closely, my laser is hovering around the caved-in surface of the mirror, and this caved-in surface will be my reflecting surface. Obviously, this surface is towards the center of the sphere of which this mirror is a part. Concave mirror is also called as a converging mirror. We will study about it later. Moving on to convex mirror. Convex mirror is that mirror wherein the reflection of light takes place at the convex surface or the bent out surface. The reflecting surface is away from the center of the sphere of which the mirror is a part. If I make up my whole sphere, I can see that the reflecting surface is outside, or it is the bent out surface or the caved out surface, and it is away from the center of the sphere of which this mirror forms a part. Convex mirror is also called as a diverging mirror, which we will again see in the later slides. Let us now study some important definitions which are related to the terms that describe the spherical mirror. Here I have both the spherical mirrors, the concave and the convex, and different terms that are going to describe my mirrors. The first one is the pole P. The pole is the central point of the reflecting surface of the mirror. The next one is the center of curvature, that is C. The center of sphere of which the mirror forms a part is called the center of curvature. The next one is the radius of curvature. The radius of curvature is the radius of the sphere of which the mirror forms a part. You can see the radius of curvature of the concave mirror over here and the convex mirror over here. Principal axis. Principal axis is the straight line joining the pole and the center of curvature of the mirror, and it is extended on both the sides. Over here we can see that PC, which is extended on both the sides, is called as the principal axis. Next is aperture. The diameter of the periphery of the mirror is called aperture. Over here, if I join the two endpoints of this mirror, this diameter is going to be called as the aperture. Principal focus. The point on the principal axis at which the light rays parallel to the principal axis after reflection from the mirror actually meet or appear to come from is called the principal focus of the mirror. Here, point F is nothing but the principal focus of the concave mirror over here and the convex mirror over here. The next definition being focal length. Focal length is the distance of the principal focus from the pole of the mirror. Over here, FP or PF forms the focal length of the mirror. The last one being focal plane. The plane perpendicular to the principal axis and passing through the principal focus is called as the focal plane of the mirror. Over here, if I have a plane which is passing through the focus and which is perpendicular to the principal axis CP, that is going to be my focal plane. It is worth noting that a line drawn from the center of curvature to any point on the spherical mirror is normal to the mirror at that point. So suppose if I draw a point from C to any other point on this spherical mirror or maybe on this spherical mirror, that line is going to be normal or perpendicular to that point of the spherical mirror. Let us now discuss a bit on the principal focus of these mirrors. What you see here is the concave mirror. In this figure we see that a number of rays parallel to the principal axis are falling on the mirror. These rays that are parallel to the principal axis CP are also called as the paraxial rays. If we now observe the reflected rays, we see that they are all intersecting at a point F on the principal axis. This point is called as the principal focus of the mirror. Now, suppose if the point source is at the principal focus of the mirror, we will see that by the principle of reversibility of light, that the reflected rays are parallel to the principal axis. This action is called as collimation. Moving on to the convex mirror. In case of convex mirror, the rays get reflected at the reflecting surface of the mirror, and these reflected rays appear to come from a point F on the principal axis, and this point F is called as the principal focus of the convex mirror. Similarly, if the light rays incident on the mirror in such a way that they seem to be converging at the principal focus, the reflected rays are collimated, which means that the reflected rays are parallel to the principal axis. It is worth noting that the concave mirror is called as the converging mirror because all the paraxial rays that are incident on the surface of the concave mirror meet or converge at the focal point or focus of the mirror. Similarly, it is also worth noting that the convex mirror is called as the diverging mirror. This is so because the paraxial rays of light after incidence is reflected, scattered or diverged from the reflecting surface. But what is worth noting is the fact that when we extend the reflected rays backward, all the reflected rays or the divergent rays appear to meet at one single point that is called as the focal point or the focus of the convex mirror. Let us now study the rules for image formation by spherical mirrors. These rules are basically rays of light that have to be considered so as to study how an image is formed when the object is kept at different positions with respect to the pole P, the focus F, and the center of curvature C. There are four rays of light that we can consider when we have to study the image formation. But out of these four, we can liberally choose only two. It is worth noting that when we draw a ray diagram, we have to represent the ray by an arrow. Let us move ahead and see those four different rays. The first ray. The first ray of light is parallel to the principal axis of the mirror and it passes through its focus after reflection from the mirror, as shown in these two figures below. From the figure above, it can be clearly seen that the light ray passes through the principal focus in case of the concave mirror and it appears to diverge from the principal focus in case of the convex mirror. Let's move ahead to ray number 2. Ray number 2. The second ray that we can consider is the ray of light passing through the center of curvature of the concave mirror or is directed in the direction of the center of curvature of a convex mirror and it is reflected back along the same path as shown below. Now this happens because the incident ray that falls on the mirror lies along the normal to the reflecting surface. Moving on to the third ray. The third ray is the ray of light which is passing through the principal focus of a concave mirror or a ray of light which is directed towards the principal focus of a convex mirror. And this ray after reflection becomes parallel to the principal axis as shown in the figure below. Moving on to the fourth ray. Now this ray can be any ray that is incident obliquely onto the principal axis and strictly towards the point P, that is the pole of the mirror, on the concave mirror or the convex mirror, and it is worth noting that this ray is reflected obliquely as well. Now the incident ray and the reflected rays follow the laws of reflection at the point of incidence, which is the point P or the pole of the mirror, and thus it makes equal angles with the principal axis as shown in the figure. Let us now study the image formation by spherical mirrors. First, we take up the image formation by a concave mirror. Now the type of image formed by a concave mirror depends on the position of the object that is kept in front of the mirror. We can place the object at the following places which will be shown in the upcoming slides. We start off by the farthest distance of the object from the mirror, that is no prizes for guessing, infinity. Moving to its closest distance from the mirror, that is between the focus and the pole. Since you have already covered this in your lower classes, I am going to take this up swiftly. Let us consider the first case when the object is somewhere at infinity. The ray AB and DE are the two incident rays which are paraxial. After reflection, both the rays pass through the focus. Thus, obviously we feel, or rather we understand, that the position of the image which is thus formed will be at the focus F. As you can already see, the size of the image is extremely diminished. In fact, what we see over here is that the image is a point-sized object. The nature of the image is that it is real and inverted. It is worth understanding that the images which are formed in front of the mirror are going to be real images and the images which are formed behind the mirror will be virtual images. Let us consider the second position. The object is kept beyond the center of curvature this time. Now, as said before, the two rays that we can consider would be The first ray, that is paraxial, which is parallel to the principal axis. Now after reflection, this ray passes through the principal focus of the mirror. The second ray that we can consider will be the ray of light that passes through the center of curvature of the mirror and follows the same path back after reflection. The point of intersection of both of these reflected rays can be marked, and a straight perpendicular line can be drawn from the point of intersection of both the reflected rays down to the principal axis. Now, how do we decide on drawing the arrow? We look at something which we have already studied in the lower classes, that is the test of similarity of triangles. What we see over here in triangle ABC and triangle A-B-C, that angle C is congruent or same because these two angles are vertically opposite angles and they are congruent. What we also see is that angle B dash is equal to angle B because both of them are 90 degrees. By this we come to the conclusion that angle A has to be equal to angle A dash. And while writing similar triangles, we write it as triangle A, B, C is going to be similar to triangle A dash, B dash and C, and not maybe C, B dash, A. Thus, if arrow marks towards A, the arrow has to mark towards A dash as well. This is how we draw the formation of an image. Now let us look at the characteristic of this image. The position of the image thus formed is going to be between the focus F and the center of curvature C of the mirror. We clearly see that the size of the image is diminished and the nature of the image is real and inverted. Had this image been upright or erect, we'd have called it otherwise. Moving on to the third position of the object, that is at the center of curvature C. So let AB be the object. Again we consider two rays, but this time the first ray is going to be paraxial. So after reflection, it touches the focus. The second ray is going to be the ray which is passing through the focus after reflection. This ray becomes paraxial. Now what do we see here? The point where both of these rays meet is exactly opposite to the point of the object. Thus, we draw the perpendicular line over here. And after we draw this, we can clearly infer that the position of the image thus formed is at the center of the curvature itself. The size of the image is same as that of the object, but the nature of the image is real and inverted. Moving on. Now let the object be placed between the center of curvature and the focus F. Again we take two rays. The first ray is the paraxial ray AD, which after reflection passes through the focus. The second ray is AE, which is passing through the focus and after reflection becomes paraxial. Again, we mark the point of intersection of both these reflected rays and mark down the projection on the principal axis. By similarity of triangles, we get that A dash B dash is the image of the object AB. We also see that the position of the image is beyond the center of curvature. The size of the image is clearly enlarged and the nature of the image is real and inverted. Oh, are you seeing a concurrent pattern here? If not, wait to find out more. Let us consider the fifth position now. That is, when the object is placed right at the focus of the concave mirror. We again take two rays, one which is passing through the center of curvature after reflection follows the same path back, and the second which is paraxial and after reflection passes through the focus. We see that these two reflected rays are parallel to each other. And obviously, what will happen to the position of the image? The position of this image will lie at infinity. The size of the image is going to be extremely large, and the nature of this image is going to be real and inverted. Moving on to the sixth position, that is when the object is placed between the focus F and the pole P of the mirror. Oh, what do we see? We take two rays again. The first ray which passes through the center of curvature and the second ray which is paraxial. After reflection passes through the focus again. We clearly see that these two reflected rays do not meet. But what if we extend the reflected rays behind the mirror? Oh yes, we see that after extending these rays behind the mirror, the rays certainly meet at a point. Also, by the similarity of triangles, which is between ACB and A-CB, obviously A' is going to be the reflection of A. Thus, the arrow is marked here, and we infer that the position of such an image is going to be behind the mirror. The size of the image would be enlarged, and the nature of the image would be virtual and erect. We clearly see that it is virtual because the image thus formed is behind the mirror, and it is erect because it is on the same side as that of the object. Let us now summarize about the image formation that we studied from a concave mirror. In summary, we see that as the object comes closer to the mirror from infinity up to the focus, the nature of the image seems largely real and inverted. But what is interesting to note is that the position of the image goes from the focus up till infinity. That is, the image starts moving farther and farther away from the mirror as we bring the object closer to the mirror up till the focus F. What we see here is that when the object is kept at infinity, the image thus formed is at the focus, the size of the image being highly diminished or point-sized. When the object is kept beyond C, the position of the image is between the focus and the center of curvature C, the size of the image being diminished. It grows. Now at the center of curvature, the position of the image is at the center of curvature itself, and the size of the image is of the same size as that of the object. Now when the object is kept between the center of curvature and the focus F, the position of the image thus formed is beyond C, the size of the image being enlarged. Now, when the object is placed at the focal point F, the position of the image is formed at infinity. The size of the image is highly enlarged. There is only one single position in which the image is virtual and erect. This is when the object is between the focus and the pole of the mirror, that is, the object lies very close to the mirror. In this case, the position of the image is behind the mirror and the size of the image is enlarged. You know what? Do this experiment. Look at your image when you place yourself at different positions with respect to the concave part of the spoon. Do this and let me know. Moving on to some application of concave mirrors. Concave mirrors are used as shaving mirrors, reflectors in car headlights, hand torch and table lamps, dentist mirrors, dish antenna, etc. Large concave mirrors are used in the field of solar energy to focus sun rays on an object that is to be heated. As you can see here, this is the dentist mirror by which they are testing the teeth. This is another, it is a burning mirror. This is a concave mirror and the torchlight. This is a solar cooker as you can see here, and this is the headlight of a car. Moving on, let's discuss about the image formation by convex mirrors. Convex mirror has its focus and the center of curvature behind it. So, no light can pass through and go behind the convex mirror. Thus, all the rays that we show behind the convex mirror are virtual and no ray actually passes through the focus and the center of curvature of the convex mirror. It is interesting to note that the extension of the rays that we are going to draw behind the mirror is shown in dotted lines. This is because the rays are virtual. There are two positions that we are going to consider in case of image formation by convex mirror. The first position will be when the object is kept at infinity. We take two rays. Both the rays are paraxial rays. After its incidence on the mirror, both the rays get reflected and appear to diverge. But when we extend both these rays backwards, as you can see in these dotted or dashed lines, the rays appear to meet at the principal focus of the mirror, which is behind the mirror. Thus we see that the position of the image formed is behind the mirror and at the intersection of these two reflected rays, which is at the focus. Now the size of the image is that it is highly diminished. In fact, we see that it is a point-sized image. Now the nature of the image is that it is virtual and erect. Virtual obviously because it is on the other side or it is behind the mirror. Moving on to the next position, that is when my object is kept anywhere between infinity and the pole of the mirror, there is only one inference that can be found out. Over here, we take two rays again for the image formation. The first ray is the paraxial ray, and after reflection, it appears to diverge. The second ray is the ray which is going to pass through the center of curvature of the spherical mirror. Again, since we have extended both these rays behind the mirror, they are shown in dotted or dashed lines. Now the point which is the intersection of both of these reflected rays, we mark this point as A dash. By the similarity of triangles, that is A, B, C is similar to A dash, B dash and C, we obviously mark the arrowhead at A dash. And thus we see that the position of the image is clearly behind the mirror, strictly between the pole and the focus F. Now the size of the image is diminished and the nature of the image is virtual and erect. You know, convex mirrors are used in the rear view mirrors of the automobiles. Do you know why? This is because the image that is formed appears closer to the mirror than the actual object, and we can see a wide variety of the other cars as well, because all of them would appear closer to the mirror. Let us summarize. In summary, we see that when the object is kept at infinity, the position of the image formed because of the convex mirror will be at the focus F behind the mirror. The size of the image is going to be highly diminished, the nature being virtual and erect. And when we bring the object anywhere between infinity and the pole of the convex mirror, the position of the image strictly lies between the pole and the focus F of the mirror, that too behind the mirror. It is seen that the size of the image is diminished and the nature is virtual and erect. Thus, whatever be the position of the object in front of the convex mirror, the image formed by a convex mirror is going to be always behind the mirror. It will be virtual, erect, and obviously smaller than the object. Now, what are the applications of convex mirror? As I already told you, convex mirrors are used as rear view mirrors in automobiles to see the traffic at the back side, as they give absolutely erect images and also highly diminished ones, giving the wide field view of the traffic behind. Let us have a look at how these mirrors look like. You know, convex mirrors are also used for security purposes. Google it up and find it out. For now, we conclude here, and for the next topics, we will be putting out another video soon. Till then, bye bye and take care.